How does a rocky world survive such closeness to a restless red star? Can gravity, heat, and time agree on one surface? Kepler 186c turns quietly, holding its answer for later. Settle in now, and imagine starlight arriving tired and ancient. A telescope noticed rhythm where darkness briefly increased. That rhythm marked a planet crossing, repeating patiently, measurable, undeniable, precise. This planet circles a red dwarf, small, cool, long-lived. Its light is gentle, yet distance is unforgivingly short. Energy accumulates there, shaped by proximity rather than stellar power alone. Kepler 186c is slightly larger than Earth, heavier and denser. Gravity presses downward with quiet insistence on every surface. Even mountains would feel heavier there, compressed into patient stillness. Its discovery surfaced in 2014, hidden within archived data. Brightness dipped by less than 0.1%. Such subtle loss of light revealed a world without ever seeing it. 580 light-years separate us from this system. The light began traveling before modern science had language. Observation here is listening to the past with calibrated instruments. The orbit is fast, only 7 Earth days long. Time there feels compressed, seasons unable to form. Repetition dominates, a loop enforced by gravity's efficient design. Distance to its star is only fractions of an astronomical unit. Heat gathers faster than it can escape. Temperature stabilizes high, not by fire, but constant exposure. Models suggest tidal locking, one side facing light forever. The opposite side waits in endless darkness. Between them, gradients stretch rock, atmosphere, and structure silently. Atmosphere survival is uncertain under persistent stellar radiation. Lighter gases may drift away into space. What remains depends on mass, magnetism, and time's erosion. Gravity on Kepler 186c pulls harder than Earth's familiar hold. Every structure would feel heavier, movement slower, pressure constant. Rock responds differently under stress, folding inward, resisting height and sharp relief. Mass estimates suggest internal heat retained efficiently. Energy trapped beneath the crust seeks release through fractures. Volcanic activity becomes not dramatic, but persistent, reshaping surfaces over time. Such pressure alters chemistry deep below. Minerals align differently, melting points shift subtly. The planet's interior behaves like a patient engine, never fully resting. The orbit is not perfectly circular, only slightly stretched. This small eccentricity changes heating across each revolution. Temperature rises and falls rhythmically, stressing crust and mantle repeatedly. No long seasons form here, only cycles of exposure. Climate, if it exists, follows gravity rather than axial tilt. Environmental stability becomes a narrow balance between extremes. Repeated heating weakens surface materials gradually. Expansion and contraction fracture stone microscopically. Over time, landscapes would soften, collapse, and reform continuously. The host star burns cooler, but closer distance changes everything. Radiation arrives concentrated, persistent, unavoidable. Energy delivery depends more on proximity than stellar temperature alone. Red dwarf activity can be erratic over long timescales. Stellar emissions may strip atmospheres slowly. Survival depends on magnetic shielding and gravitational grip working together. If the atmosphere is thinned, surface conditions shift rapidly. Heat escapes unevenly, nightside cooling sharply. Balance becomes fragile, sensitive to even small energetic changes. Tidally locked rotation freezes one face toward the star. Day never ends there, night never begins elsewhere. Time divides the planet into permanent hemispheres. Between light and dark, transition zones may form. Temperature gradients stretch winds and pressure systems. Movement becomes a response to imbalance rather than rotation. This configuration shapes every long-term outcome. Geology, atmosphere, and surface chemistry align with orientation. The planet becomes defined not by distance, but by facing. Atmospheric escape begins quietly, particle by particle. High-energy radiation lifts lighter gases beyond gravitational hold. Over billions of years, even thick skies can thin into absence. Hydrogen is lost first, then helium follows. What remains grows heavier, denser, and chemically altered. An atmosphere becomes less protective, more reactive, and increasingly fragile. Without insulation, heat behaves unevenly across hemispheres. Dayside traps energy, nightside releases it rapidly. Stability erodes through imbalance rather than sudden catastrophe. The star itself is older than our Sun. Its long lifespan allows extended exposure to radiation. Time here acts slowly, but with cumulative authority. Low metallicity shaped the system's early formation. Heavy elements were scarce, yet planets were still assembled. This challenges older assumptions about planetary construction thresholds. Kepler 186c formed efficiently, despite limited materials. Mass concentrated, gravity strengthened, structure stabilized. Outcome depends less on abundance, more on organization. The inner system is tightly packed, almost crowded. Neighboring planets pass relatively close during orbits. Gravitational interactions subtly reshape trajectories over long durations. Such proximity increases orbital sensitivity. Minor shifts amplify through repeated cycles. Stability becomes a negotiated agreement rather than a fixed state. Despite this, the system persists calmly. Motion remains ordered, predictable, mathematically restrained. Chaos here is limited, controlled by resonant balance. Kepler 186c is not within the habitable zone. Liquid water cannot persist on its surface. Heat overwhelms any long-term chemical equilibrium. Comparison with its outer sibling highlights contrast. Distance alone transforms planetary destiny. Small positional differences rewrite entire environmental narratives. This world teaches through extremity, not comfort. It reveals limits imposed by physics. Understanding comes from observing where life-friendly conditions fail. Transit depth measured only 0.07% consistently and always precisely. Such small dimming demanded extreme instrumental precision and calibration discipline. Detection relied on repetition, patience, and statistical certainty over years. No image confirms this world visually today. Everything known emerges from indirect measurement and modeling. Reality here is reconstructed, not seen, assembled carefully from light behavior. This limitation forces science into humility. Certainty becomes probabilistic, never absolute. Understanding grows through convergence of evidence rather than single observation. Now we return to the opening question. How does such a planet survive extreme closeness without collapse? The answer lies not in violence, but equilibrium. Gravity counters heat through structural compression. Rapid orbit stabilizes energy input into predictable cycles. Tidal locking prevents chaotic redistribution, enforcing long-term balance. Survival here means endurance, not comfort. Physics allows persistence even under harsh constraints. The planet exists because forces cancel, not because conditions are gentle. Kepler 186c survives by being exactly what it is. Not Earth-like, not habitable, not forgiving. Just stable enough within strict physical boundaries. Its closeness defines every property we observe. Heat, gravity, atmosphere, rotation all trace back inward. Distance becomes destiny written early and enforced forever. The mystery resolves quietly. Nothing miraculous is required. Only balance, repetition, and time doing what physics allows. This world teaches through contrast rather than hope. It shows where life cannot persist easily, and why rules matter more than exceptions. Kepler 186c is a boundary marker, a reminder of limits drawn by nature. Understanding grows clearer at edges, not centers. As attention softens, the investigation rests. Facts settle like sediment after motion. What remains is clarity, not noise. If this journey through balance, heat, and gravity reshaped how you feel about distant worlds, subscribe, like, comment, and share. Science deepens when curiosity slows. Let others enter the sleep lab too.